Welcome to this series on process intensification and flow chemistry. I am Professor Anil Kumar from IIT Bombay, and this is part 1 of the series. This series is divided into 3 broad themes. First, deals with what is the process intensification. Though this theme sounds very simple, most of us have forgotten what is the physical significance of process intensification. Therefore, I will spend some time in refreshing our high school chemistry to understand what is the physical meaning and the significance of process intensification. The second theme will be what is continuous flow chemistry. Since this is a new topic and very different from batch chemistry, we will move slowly through this theme to make sure we all understand the nuances of continuous flow chemistry, its distinct advantages and differences with respect to traditional batch chemistry. The third theme will be what is the connection between continuous flow chemistry and process intensification. Here, we will learn how to incorporate continuous flow technology for process intensification. We will take examples from both academic as well as industrial domains on the applications of continuous flow chemistry for process intensification. We will also learn about the new avenues which become available to synthetic chemists, which were elusive in traditional batch chemistry. Process intensification has various components and hence can be defined in multiple ways. The most important and broad definition of process intensification is to improve the rate of the reaction without compromising safety. This automatically translates in an increase in process throughput. Another definition is improvement in the process controls. This, in turn, helps in improving safety and also decreases the batch failure rates. Third definition is improvement in modularity. This helps in improved maintenance, replacement, and relocation of the plant. Fourth definition is improvements in the handling of runaway reactions. This is the most dangerous part of a chemical factory, and hence, controlling this is extremely critical for process intensification. Next definition is the decrease in effluent. This is one of the major concerns for the present-day chemical factories. With increasing tightening of regulatory norms, it is desirable to reach the zero effluent production state at the earliest. Sixth definition is the decrease in carbon footprint. If we can improve our processes with a lesser load on the cooling component of the utilities, we can significantly reduce the energy requirements. The final definition is how to decrease the batch size. In the traditional batch chemistry, the cost of production per unit decreases as the batch volume increases. However, the large batch size is very dangerous in situations like batch failures or runaway reactions. Therefore, it will be highly advantageous if one can decrease the batch size while retaining the same production capabilities. It is clear from the above discussion that there are multiple ways by which one can define process intensification. I feel improving the rate of the reaction is the broadest definition, wherein all other definitions are automatically incorporated. Therefore, in our subsequent discussion, we will focus mainly on what is the rate of the reaction, which are the factors which affect the rate of the reaction. We will then discuss the main limitations of batch technology, which prevent the ultimate process intensification, and how these limitations can be overcome using continuous flow chemistry. Rate of a chemical reaction and its implications in process intensification is one of the most underutilized concepts by process chemists. Most of us have forgotten this concept, as it was taught to us way back in our high schools. Since we learned many more advanced topics in organic synthesis in later degrees, we have forgotten the physical significance of rate of the reaction in day-to-day process intensification. Let's us learn this concept again. But with the perspective of process intensification. As we all know, rate of a reaction is represented by Arrhenius equation, as shown here. Using this equation, one can infer that rate of the reaction, which is nothing but the number of molecules reacting per unit time, can be correlated to two parameters. The first factor, represented by A, is the fraction of effective collisions. The second factor is the fraction of molecules having energy equal to or higher than the activation energy. This can be easily confirmed by equating the physical units on both sides of the Arrhenius equation as shown here. Based on Arrhenius equation, if one has to increase the rate of the reaction, one has to either increase the number of effective collisions or the fraction of molecules having required activation energy, or both. Now, we know what needs to be improved. We will learn how to go about improving these parameters. At this stage, we have learned what is the process intensification, and what is rate of a reaction, and how the two are related. We also know how to increase the rate of the reaction. Now, we will focus another simple concept, which is what is a chemical reaction. One of the most simple definition is the process wherein one breaks and forms chemical bonds. If so, then we all know that breaking or forming of the chemical bonds require rearrangement of the electrons and orbitals. The process by which electrons and orbitals rearrange are vibrational and rotational motions. We all know that the time scale for these vibrational and rotational processes are sub-picoseconds or in femtoseconds. Therefore, if the reaction has to happen between two molecules, it should happen in femto to picosecond time interval. Therefore, based on our understanding of various chemical events, we agree that a chemical reaction should happen in sub-picosecond. However, in real life, the situation is very different. We carry out reactions in the time domain of hours to days. I am sure it is very shocking to many of you that the process, which actually happens in sub-picoseconds, is being carried out in hours and days. It is amazing that for over a century now we have been doing chemistry at a timescale which is 12 to 18 orders slower. I should point out here that there is a real reason why chemistry is being practiced at such slow timescales, though we have forgotten it and taken this as granted. We will discuss these issues now. The primary reason why we practice chemistry at such a slower time scale is because of the technology limitations. We use batch reactors, which have serious heat transfer limitation. So the use of batch technology is the main reason for doing chemistry at such a slow rate. I am sure that many of my chemist friends are very happy that it is a technology-related problem and not a chemistry problem. I would like to point out here that the chemists are the one who develop the very first process in lab and then hand over their development to process engineers for production. The inability of the lab chemists to do process intensification and scale up is because of the complications in batch scale up. I can assure you all that it will be possible for the chemists now to take their development from lab to all the way to production after successful completion of this course. Let us now explore this heat transfer limitation issues, which hamper the process intensification via batch technology. In the simplest explanation for a safe process, the rate of the generation of heat should be less than that of the rate of heat exchange. In a chemical process, the heat is generated by the reacting species, while the reactor and utilities take care of heat transfer. Now we will look more deeper as why batch technology has poor heat transfer rate. As can be seen here, the heat exchange can only happen from the surface of a batch reactor, and therefore, it depends upon the surface area of the reactor. It is also clear that the heat is generated by the reacting species, which are present inside the reactor, or the volume of the reactor. Therefore, the net heat transfer rate is related to the surface area to the volume ratio of the reactor. For a given reactor and utility, this ratio is fixed. This means, we can easily calculate as what is the maximum heat my reactor and utility combination allows me to exchange per unit time. Now, for any controlled process, I have to make sure to control the rate of the reaction such that the heat generated per unit time is less than the heat exchange capability of the tools used. This is the most critical parameter which process engineers have to keep in mind. If this is violated, it will lead to runaway reactions and hence accidents. In order to make it more easy to understand, let us do an exercise by taking a hypothetical reaction wherein the heat generated by the reacting species is 200 joules per gram. Let us also consider that our reactor and utility combination have a maximum heat exchange rate of 500 joules per hour. Now, in order to do this process in controlled fashion, we have to make sure that the heat generation is less than the heat transfer. In other words, the maximum rate of the reaction is 2.5 grams per hour. Therefore, the interplay of the heat generation and heat transfer dictates how much a process can be intensified. I am sure it is clear by now that the real rate of a chemical reaction is in sub-nanoseconds. If we let the reactions to take place in this time domain, large amount of heat needs to be exchanged per unit time. This is not possible for a conventional batch reactor, and hence, the only way to develop a controlled process is to slow down the reaction to hours or days. At this stage, we have understood what is process intensification, how it is related to the rate of the reaction, and how the rate of the reaction is limited by heat exchange capabilities of the reactor and utility combination. It is now clear that we need to slow down the reaction significantly in order to remain in the safe zone. The most common methodology to decrease the rate of the reaction is by dilution. This decreases the fraction of effective collisions and hence rate of the reaction. However, the negative effect of this is decrease in throughput and increase in effluent. Another method to decrease the rate of the reaction is by decreasing the reaction temperature. This leads to decrease in the fraction of molecules with required activation energy. Therefore, we can either decrease the temperature or increase the dilution, or both in order to slow down the reaction. I am sure you all know by now that why we practice chemistry at such a slower time scale compared to the real rate of reaction. This means the confusion we had is no more and we are all happy now. Now, let us look into how to increase the rate of the reaction, which in turn leads to process intensification. We have to increase the number of effective collisions and the fraction of molecules having required activation energy. Also, denote that the maximum rate which one can achieve is limited by the surface to volume ratio of the reactor. I am happy to inform you that the recent developments in process scale-up via continuous flow tools provide us much higher heat exchangeability compared to conventional batch reactors. Therefore, continuous flow processes enable us to carry out reactions at much higher rate. Let us summarize the main learnings from this module. First is that the process intensification is related to rate of the reaction. Second is that the rate of reaction is given by Arrhenius equation. We also learned that the actual reaction happens in sub-nanosecond time domain. However, we do not practice chemistry in this time domain due to the limitation of the heat transferability of the tools, which depends upon surface area to the volume ratio of the reactor.